Stanford University.
Thanks very much. I'm very tickled that you're here because I know I'm competing with a football game, the start of a baseball game. So I'm keeping a very close eye on the time because I know the first pitch is at 4:57. So I want to be out before then. And I'm also competing with the rain. And then the first thing is I'm talking about mathematics, which generally is something that people want to escape from after college, not revisit at a homecoming weekend. But my purpose for this afternoon is really sharing with you a bit of the passion that I have for computational mathematics. And as Adam was saying, I'm directing quite a large institute now on campus. It's the Institute of Computational Mathematical Engineering. And you may not have heard of that because we haven't actually been in existence all that long. There was a precursor to this institute, which was a program in computer science, and I actually did my PhD in that program, so I'm an alumna myself from '96. And I was fortunate enough to come back here in 2001 as a faculty member after getting my PhD in computer science in energy resources. Don't ask me how that happened, but they allowed me back in. And since 4 weeks, I'm director of this institute. But we have 140 graduate students, 70 masters and 70 PhDs. We have no undergraduate students, but we're teaching 20 courses in the School of Engineering, for Earth Sciences, for Applied Mathematics, and so on, for the whole university, 4,000 student units. And so most of the the mathematical harassing of undergraduate and graduate students is led by my institute. And so that's a wonderful feeling to be able to control that, for some people, very painful experience. But I love it. And I've always really loved mathematics, and I want to show you a little bit today why. And one of the reasons why I absolutely love this is on the board right now, and that's a whole bunch of complicated equations. And those are the equations we're going to be talking about today. But my idea is that I make this much simpler for you. Because really, when you look at it very carefully, all of the equations that govern fluid flow processes, be it climate models, weather models, optimization of sail design for competitive yacht races, one of the things I've done. Another thing I've done is optimizing wings for pterosaurs. Of course, they don't exist, but we've just made up some for National Geographic. I've also done fluid flow in oil and gas reservoirs, aquifers, groundwater models. All of these processes that may seem completely different are all governed by these equations. There's all the same stuff. And then they look very complex, right? And this is, of course, what we like. We like to use Greek symbols. We like to use long mathematical expressions so we can impress people at Friday beers and so on. You know, sometimes we even put it on T-shirts and have something like, nah, we understand this and you don't. But really, when you start looking at it and breaking it down, it's all relatively simple. And it's really quite wonderful when you see how all of these fields, you know, coastal oceans, wind turbine optimization, you name it, is all connected in exactly the same way. And this is one of the reasons why I love computational mathematics and why in the 25 years or so that I've been doing this professionally, I've worked on 10, 12, 13 different projects, all sorts of different fluid flow problems. And sometimes when people look at my CV or my publication and say, you're crazy, you know, you're all over the place. I say, no, I'm always doing just this. And so that's what I'd like to share with you. So by the end of this hour, you're either going to tell yourself that you will never ever do a math course, classes without quizzes again at a homecoming weekend, or you're going to be so excited that you'll come back next year and apply to do a master's in my program. Right? It's normally either or, okay? So I'm hoping to see you all back next year for masters. It actually happened once, about 5 years ago. I gave a talk at homecoming weekend, and there was somebody in the audience who was 84 years old and decided at the end of the talk that he wants to do another PhD. Had a PhD already from Stanford in physics from 1954, I think it was. And he came back and he started it, but unfortunately it was a little bit too fast for him, but he did take some of my courses, which was absolutely fantastic. Anyway, so let's go and look at these equations. So here they are. And they, like I said, these equations govern fluid flow no matter where the fluid flow is. You know, sometimes the equations look slightly different, but in concept they're all the same. So I wanted to tell you a little bit about it, and I won't raise the screen right now. I'm just going to write here because, you know, I am just... Right. So let me start here. There is a couple of things in these equations, right? A couple of terms. And when we understand these terms, let me put one other down here, you've understood all these equations. And then I can start talking about how to solve these on a computer, because ultimately that's what we'll do. Okay, so I will move between blackboard and screen for a bit, because, you know, this is a math course, so obviously I have to use this blackboard. Okay. Now, what are all these things here? U is stuff that we're interested in knowing. Now, when you think about fluid flow, what could U be? U is just a name for something we're interested in when we're looking at fluid flow, something that describes ocean flow, wind. What could U be? For example, energy, or velocity, volume we're leaving, pressure. If we had all of that, right? If we had, and we're assuming that density does not change, so we're not taking that into account right now. But if we knew how the velocity changed as I'm traveling through space or as time changes, if I know how the pressure behaves in a system, and if I knew how energy behaves, so what the temperature was like, then the miraculous thing is I can really describe this whole process, and moreover, I can predict it. Because think about, for example, airflow, like this in a room. Okay? So we opened some windows, and there was a nice breeze outside. We could maybe feel the air move in this room. What drives that air? Now, what is causing it to move? Difference in pressure. Now you could say, well, it's the wind outside, right? But ultimately that wind is driven by pressure differences, low pressure, high pressure. What else? Ultimately by the summer, we're not going to go that far. I want to keep the computations a little bit less than the solar system, because then maybe we have a chance to actually simulate it. Sure, size of the opening, so configuration, right? You know, how things are moving is dependent on the configuration of my room. In other words, on the boundaries that I have in that flow domain, you know, if you understand that lingo. Well, how about gravity? You know, you can say gravity doesn't really play a big difference. If I have an air molecule flowing around, it's not going to just drop down, right? But gradually, gravity will also influence things. So things move because there is a force acting on them, right? And as a result of this force, things change. Velocity changes. When things start to heat up somewhere, it can maybe have a density change. It can have energy change, because things can start flowing faster. So kinetic energy changes and so on. So all I really need to understand of any fluid system is what's in that system, what's going to be moving or changing that I'm interested in. And most of the time, that is just... that's my U. That is things like pressure, velocity, and most of the time we don't think just about velocity, but we actually think about something called momentum, which is nothing but a mass.
Funny thing is that at the surface of the wing, the air is actually not moving at all. It's just changing very, very quickly from 500 miles per hour to 0 in a very thin layer over that wing, which we call a boundary layer. So it's got very, very strong pressure or velocity change in that very thin layer. There's a lot of force on that wing as a result of it. Right? That wing is really stopping that flow, and you can just imagine if you're trying to stop a runaway train, there's a lot of force on you. It's the same on that wing, right? But luckily we know how to engineer these things. So we have maybe some boundary forces. Okay. And all of these things here, they determine how you change. So let me just write down. It determines how you changes, be it pressure, momentum, energy, whatever, as a function of time, right? So how it changes in time, how fast it changes, how slow it changes, how long does it take for it. Maybe it doesn't change at all. And also as a function of space. Because not everywhere in my domain, I may have the same velocity or the same pressure, right? So if I look at weather, we have nice low pressure here now, and somewhere else maybe high pressure. So it changes also as a function of space. Now, this is really all we need to do and all we need to know. We not just need to set up some equations that describe this, equations that say, if I have a strong pressure gradient, so my pressure somewhere is high and very close to it is low, what do you think will happen to the air velocity? It's going to be high, right? Because I have a strong force pushing that air from high pressure to low pressure. So I have a strong wind. So I need an equation that says this. A high pressure gradient gives me a strong high velocity. I need to have things like, if gravity is strong, then my downward velocity, my vertical velocity will grow. Things will start to fall. If I have skin friction at a boundary, then near that boundary, my flow will need to slow down. That's all we do. It's just a bunch of rules to govern the behavior, very natural, intuitive behavior of this fluid flow. So we look at the fluid problem. We write down the sort of things that we want to understand about this flow. We write down all of the forces that we can think of that may drive that flow. Sometimes we throw some out, because not all of them may be important, right? For example, in this room, if I did airflow in this room, I would leave out gravity. Sure, it has some influence, but it's so tiny compared to any drafts or other winds that I may feel in this room that I can throw that out. So we look at it, we simplify, and then we decide how this changes. And the ratio, these rules that say, if my pressure gradient, my pressure force is this big, then it starts to flow this fast or that fast. Well, that I just know from experience. That comes from experimentation, because that depends on things like viscosity of a fluid and so on. But really, all of these rules, the general behavior is very intuitive. Pressure gradient higher, flow stronger. But how much stronger, what that ratio is, that is something we just get from experimentation. There's no rocket science involved with that. Okay? So we look at tables and other things, and we just write down equations. Now let's look at this a bit. It determines how you change as a function of time or function of space. That stuff, function of time, function of space, is in symbols like this. So if I see du dt, what that says is, how much does u change with respect to a change in time? The little delta is just a change in. So if I translate this in words, this just says change in u in a certain change in time. That's all. Okay? What would this say then? Yeah, so if my x direction, we are in 3 dimensions, so I have an x direction, I've got a y direction, I've got a z direction. This just says, if I walk in this direction, so I'm changing x, this is how much u is going to change. Now, right now here, nothing much is changing. But it could be that if I'm walking here, all of a sudden I'm picking up a draft from one of the open windows on that side, and I start feeling a breeze, and then obviously the velocity of the air in this direction changes, right? So that would then be u. So here it's 0, and here start picking up the breeze and say, oh, the u dx must be positive, because as I'm changing x, all of a sudden that velocity starts to grow. So that's the u dx. The u dy is the same in the y direction. I can do this for pressure. I can do this for velocity. I can do this for mass. And that's it. So as a physicist and mathematician, we just set these things up looking at these physical rules, and there come the equations. Okay? So that's the first step. It's not so hard. Can we load the screen? Go back to the presentation. Huh? B? Thanks. So now let's look at these equations that are a little bit fuzzy, which I said before is by choice, because that's how we sometimes feel about them. No, it's just because copy and paste didn't work very well from LaTeX. I don't know if you can see this, but do you see all these dt's, dx's, dy's? And what do you see? You see v's, you see little p. Guess what that stands for? Pressure. What do you think little u would be? That's a velocity, but it is one of the how many velocities do I need to describe flow? 3, right? And x and y in the z direction, so we're so incredibly creative as mathematicians. We generally call them UVW, okay? So we have x, y, z, UVW. So that makes a lot of sense. If I start to push on something, whether or not that goes real fast or not, well, it depends on whether I'm pushing air or whether I'm pushing peanut butter. Well, what's the difference between them? Well, one is a lot runnier than the other. You know, one is very sticky, and we call that very viscous. So obviously that viscosity needs to come in somewhere. Well, there it is. Now let's see if I can find some forces, right? Because these are all equations that tell me how velocity changes or momentum changes, and they can only change as a result of applying a force, okay? So where are my forces? They're hidden a little bit, but who can see some forces? Here's a little guy. This is g. G is the gravitational constant. It's multiplied by the density. This is just gravity, mg. Now, so there's a gravity force, and then I had one other force that I talked about. That was the pressure gradient. So what would be a pressure gradient? That tells me how much a pressure changes over space, right? So what would that look like? What sort of term would be the pressure gradient? dp dy, dp dx, hey, dp dx. And the pdx and the udx are in the same equation. Well, makes perfect sense, okay? So that's really it. So now we have the equations, and then the only thing that we need to think about is how do we model these? Now, you know from algebra that if you have an equation like x squared is 9, you can solve for x. Right? Can you still do that? Plus or minus 3, right? Or a more complicated one. 2x is 16, right? X is 8, right? So here in this case, though, the equations are a little bit more complicated. First of all, we've got these ddx's, ddt's all put together. Then, as you can see, we have a bunch of equations because how many unknowns do we have here? Well, we have p, we need to know u, we need to know v, we need to know w, right? So these are already 4 equations. If I have 4 unknowns, how many equations, or 4 unknowns, how many equations do I need to solve for 4 unknowns? 4. Okay, that was the easy one about algebra. It's always the same, okay? And so I have 4 equations, and are these equations independent? Can I take one and just solve it, and then I have the solution and solve the next one? No, they're all related to each other, and that makes a lot of sense, because I can't start moving things in this direction in the air without impacting flow in that direction. Now, why would that be? Suppose I was God, which I always like to fantasize about. So this is my room, right? It's filled with air. And I point my finger there and I tell these air molecules there to start moving in this direction. What do you think will happen with the rest of the room? Will I just see that flow only in this direction? I would have a vacuum there then, right? That would not be sustainable. So what would happen? Things would rush in from this side. So if I flow in this direction, I'm immediately causing a flow in that direction. So I cannot solve an equation for this direction only. It will all be coupled together, right? And so all of these systems are coupled, they're very complex, And I cannot just find a formula that gives me the solution at any point in space, at any point in time. That's impossible. In other words, there is no analytic solution to this. I cannot do what you did in algebra. Okay? So when I first saw this, I thought, for all these years, I have been taught algebra, and now I finally come to grad school, and the first thing they tell me is I can't use it. I have to go do something else. So what do we do? Well, let me go on and show you first a couple of pictures of things that I've worked on. These equations that you just saw can do things like this. Okay? So this is a vertical takeoff and landing aircraft. And you see the jets coming down. Now, what these streams are here, these are vorticity or velocity lines. But you can sort of imagine high velocity coming down. Okay, so this would be W in my equation. It would be very high here, right? This is the vertical velocity. And what is driving that? Well, a jet. And in this jet, I'm really just creating huge pressure difference that pushes that air out, right? It's just a pressure gradient that is doing this. So if I were to put the pressure here, then I see really, really high pressure somewhere there and immediately a lower pressure as that flow is pushed down. And then here it hits the boundary, and then there is a boundary force, right, that I talked about, skin friction and other things. And the flow is forced away in this direction and then becomes turbulent. And all of these things are governed by these equations. Okay? I don't need anything more for turbulence or all of that. It's all just in those equations that I showed you. With the ddx's, the ddy's, the ddz's, it's all the same. Okay? But obviously, I didn't do this algebraically. This is another example of one of my colleagues. It's just airflow past a race car. And then here you see pressure. So these are streamlines to indicate how the air is actually moving and how the particles move over this car. And here you see the pressure build up at the surface. Some areas at the surface experience a much larger force than others as this air is hitting it. It depends on how aerodynamic this car is. But again, all of this is just governed by these equations that I showed you. And they're all solved in exactly the same way. In fact, these two could be solved by the same software. This is another thing that I've done. It's looking at flow for sail design. I worked for Team New Zealand for a while for the America's Cup. If you know, who knows about the America's Cup? Oh, okay, good. Some sailors in the audience. It was wonderful to work with them. I worked on developing the Ginniker. And if you remember well, in 2000, that was the only thing that didn't break. Right? But that may be because we didn't design it very well, so that we overloaded all the other systems. You don't know that either, right? But here in sail flow, and I just show you this, again, exactly the same equations that we just had. But I show this because the behavior of the flow is very different depending on this boundary configuration. Right? So these equations are all exactly the same. But what you see and observe can change a lot. You know, with the vertical takeoff and landing aircraft, we had all that turbulence coming up. But sometimes flows are very smooth. So for example, if I'm sailing upwind, very close to the wind with my sails just act like a wing of an airplane. It's the same sort of thing. But you can see here with smoke, this is all smoke, so you can visualize how the air flows. Okay, so these are just how the smoke particles are moving. And you see that especially on the jig there, the head sail, it's very, very smooth. There's nothing turbulent there. Everything is smooth, almost as if it is attached. Here you see a little bit of a wake, a little bit of a turbulent wake where the flow is coming off. But on the downwind leg, where I have my Ginniker, when the flow hits that, I see big eddies and turbulent flow again forming. Very, very different behavior, but exactly the same equations. And you would think the same configuration because I have a boundary like a sail in both of these cases. It's just that the oncoming flow is from a different direction. And in one case, it's from a direction that is very directly aligned with the sail. And then the flow stays very smooth. It's not really hindered so much by that sail. So we call this attached flow. And in the other case, it's more like a parachute coming down where the float just hits the sail dead on, is going around it, and then the sail, with its friction on the sail surface, cannot keep that flow close to it. It's almost as if you're on your bike, your motorbike, and you're trying to go around a sharp bend, and you're going too fast, and you're flying out of the bend. What is causing that? Well, you don't have enough centripetal force, right? Not enough friction to, in other words, to balance the centripetal force. That's the same here. Airflow hits the sail, needs to go around the bend, goes really, really fast, and the sail just doesn't have enough skin friction. Now, this is a very simplistic way of looking at it, to keep that flow attached to the sail, and it flies off, it detaches, and it starts twirling around. Okay? But the same sail, the same equations, just different behavior. And I found it amazing that with that set of equations, I can do all of these different things. I'll show you a little simulation now. This is just a, if it works, yeah. This is just a simple, did you see it move? Isn't it amazing? This is my little, very simple little simulation. But here I have a downwind sail, like a ginnaker. The wind is coming in, goes around, and here it detaches. And I can, just on my little laptop, this just plays on this little thing, do these type of simulations with these equations. And then I could do more complicated things, like going into 3 dimensions and actually doing both of these sails. But now this particular simulation here that I ran for Team New Zealand would take like a week to run. It's not very good, right? So sometimes these equations, they describe everything, but they're very, very expensive to simulate. So we need to do something about it. And this is why when we're doing things like sail design, we generally just look at 2-dimensional cross-sections. And when they do wing design, they generally look at 2-dimensional cross-sections of a wing. Yeah?
Did your New Zealand work really change the look of that sail?
Did my work change the look of the sail? Not really. See, when you're working on something like this for a competitive team, what they're looking for, what Team New Zealand is looking for, is shaving off 2 or 3 seconds of a lag of the sailing race that may be 20 minutes long. They just want to shave off a few seconds, that's all. And so when you think about this, the changes that they're looking for really are very subtle changes. And I can design a beautiful sail, but if the crew is not behaving, then they won't see the 2 or 3 seconds. The errors that I'm making, because I'm using approximations, right? I'm ignoring some stuff, even when I write these equations down. Here I simulate things in windy conditions. Well, wind is gusty, and I can't predict what it's going to be over 20-minute time. So I make some approximations to the wind. They're probably off by more than the 2 or 3 seconds. So here, we always say, these simulations give me bread and butter, right, on the shelf in my cupboard. But they don't help, because I'm working in the error margin, if you'd like. But the nice thing about doing these calculations is that with a simulator like this, I can look at some really strange shapes and just play. Now, this is, the way I see it, this is not to give them the final design. That is exactly a little bit better. And it's the same in the aircraft industry. You don't use these computers nowadays anymore to get this final design that is just right. You always do that with wind tunnel tests. And then you have to go and actually fly these things to see how it really behaves, right, ultimately. But what you can do in this, it's like a virtual laboratory, right, sort of at scale. And I can put in all sorts of funky designs, be creative, and see if they do anything. I can explore, in other words, much more than I can if I have to build a scaled model and put it in a wind tunnel test, which is much more expensive. So what we do with a lot of this stuff is just play, trying out new ideas. And with the ginnaker for Team New Zealand, we did that. We tried out some new ideas. And then there's a really interesting thing, because now I can come up with a new ginnaker design. What does that mean? I can come up with a new shape, saying if you had this shape of sail, you could sail a little bit faster. Then I give it to the sail designer and say, I want this shape of sail. And they say, are you kidding me? How can I build a sail that retains that shape when I put it in the wind? Because, of course, it's a lot more complicated when you actually need to build this, right? And so there's all sorts of stuff going on. But see this more as a virtual laboratory where you can play. Okay? All right, now, let's just leave this up. But I'm going to scribble a little bit here on the side. Because we had those equations, and I told you we cannot compute this with an algebraic equation, right? So, and I've shown you results. So obviously we must be doing something to be able to compute this. But it's not a formula. And so, what do? Well, the very first thing that you do as an engineer when you have an equation that is way too complex to solve exactly, right, or algebraically, is what? You compromise, right? I mean, I call myself a computational engineer. I'm not really an applied mathematician. Because I look at these equations and say, I cannot find one formula. I'm not interested in simplifying the physics so much that I can do this analytically. I could do that. I could look at a very simple domain, very simple flow, maybe just 2 dimensions, or even just 1 dimension. People do that, 1-dimensional flow. That's kind of funny, right? So that they can find real algebraic equations that model this. But I don't want to do that. I want to have the 3-dimensional feeling of this flow, but I can't find it exactly. And I think, who cares? If I can't find it exactly, I'll find it approximately. I don't need to know exactly that it is 1.374569 meters per second. I just want to know it's around 1. That's probably enough, right? Or maybe I want to get a few floating points in there, but I don't need this completely accurately. So here is the general idea of my field. They say, okay, suppose that I want to simulate something, and it's on this domain. We're looking down on the Pacific Ocean, okay? And I want to simulate wind here. Maybe the wind sort of goes like this, okay? And all of these equations that I just showed with all the ddx's and ddt's simulate, model this. And I'm going to say to myself, I don't need to know the solution everywhere. That is the trick, right? So I want to know things only approximately. And the way I'm going to compromise is to say, I don't need to know the solution at every single x, y, z, and at every time t. I'm going to be happy if I know the solution in some set of points. Okay? And this was a fantastic idea. And the whole field of computational fluid dynamics that I'm talking about is based on it. So what they do is they divide this domain into a grid. Okay? And the idea is that at each of these intersections of these grid lines, they're called grid points, you find an approximate solution. Okay? So in 1 dimension, what would that look like? So in 1 dimension, it looks something like this. I would say we have a domain between 0 and 1. I don't find a solution everywhere, but I just find it at a bunch of points, all of these points here. And if I was looking for u of x, then now I'm saying, no, I'm not going to look for u of x as a function, but I'm going to find u0, u1, u2, for all of these points, this is x0, this is x1, this is x2, through to, well, maybe this is x capital N. And all I'm doing is finding those solutions. The un minus 1. I just find n values. That's all. Somehow. We still need to talk about how. But somehow I find them. And then I start to think, hey, the solution here, or maybe the solution here in this Pacific Ocean, through the equations that I have, of course, depends on the solutions there and there, right? For example, the velocity here will depend on the pressure I have there and the pressure I have there, but it also depends on the velocity I have there, right? Because as I said earlier, all of these things are coupled together. So when I start translating these complex equations to relationships between the U's at each of these points, I will probably get a large set of coupled equations out of it, right? But it's now just a system of equations for the U's in each of these grid points. And even if there are a million grid points and every grid point has 5 unknowns, I don't care. It's only 5 million unknowns with 5 million equations. My computers are big enough that I can solve this, no problem, right, on the computer. So the first step is that we do this, that we say, okay, instead of wanting the solution everywhere, we just want it on the grid. And then my question to you is, what if I now want to have the solution right here? Because this specifically may be Hawaii. You know, I'm interested in the wind on the big island. And it's not in the grid point. What would I do? I could take a finer grid, but I don't have enough computer power for that, maybe. I could shift the grid, I heard that, so that the grid point overlaps with that exactly, but that may be hard, because then the next thing I know, somebody in Tahiti wants to know it, and has just shifted my grid, and Tahiti is no longer on it. Okay, so I keep shifting, and don't want to do that either. But I could just interpolate, right? So if I have a solution here, 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 and here, I can probably find a pretty decent approximation to something in the middle. I can take some sort of average of them, interpolate it. In other words, if I have the solution at a bunch of points, I can probably find a solution that is okay, and that's all we're looking for, in between those points. If I want a more accurate solution, I got to compute it for more points, right? This is a simple thing. No such thing as a free lunch, right? If you want accuracy, you got to do it for more points. Now, this opens up a fantastic area. Several. One is, there are gridders that look at a domain and create a nice grid for that domain. And there's all sorts of ways you can do this. I'm a very simple gridder. I look at the domain and I want to put in straight lines like this, because I like working with these types of grids. Because computationally, they lead to simpler things. But there are people that like using triangularization. So instead of having these straight lines, they grid something like this. Anybody from near Puget Sound? So you recognize this. So this is a simulation we did on Puget Sound for tidal flow modeling. And everywhere there is a vortex of a triangle, a point in the triangle is one of these grid points. They're not as organized as nicely, but these points is where we compute a solution. And guess what? The closer we get to the land, to boundaries where things are changing faster, the more points we want. Okay? Out here, not much is happening, really. Sort of steady flow. We sort of know what it is. It doesn't change very rapidly. It just changes only with the tides. I don't have all sorts of small disturbances or turbulence or small eddies of a river coming in. All of these things happening at small scale. Don't have any of that. So I can take what we call a coarse grid here. There's only a couple of points in which I need to know the solution, and then I know it pretty much everywhere. But here, where there's a lot of stuff happening with a river coming in and all sorts of, you know, jets and eddies here, I need to have a lot of points. So much, in fact, that you can't see them anymore. Right? A lot of points there together. So this actually took one of my students about 2 months to create this grid, to get it just right. It seems very simple to do this triangularization, but there are all sorts of things you have to be aware of. For example, if I do a grid here and the triangle is completely skewed, almost squashed together like this, then my equations don't behave so well. It's just too skewed. And when I actually look at the equations and then how these equations solve themselves on the computer, I get problems. Now, I may have too big of an error. Now, so there's a whole science behind this, that when you start translating these equations on these grid points, how they behave. Okay, so but they look very fancy, I think. We like looking at these things. We've done one for Elkhorn Slough here in Monterey Bay. Right? This is the grid. And I gave you the answer, but I always ask, what's this thing? When I show that to people, that's actually the train track. it's a little bit higher. So there's no flow going there. There's just flow here in this little area here under the train. Okay, so that's Elkhorn Slough. Again, takes a long time to think of these types of grids. Here's a grid on the airplane. Now, obviously, this is not just the airplane itself that we're gridding, but also the flow around it. But I won't show you that because it's so hard to see these things grow in 3 dimensions. But in 3 dimensions, just little tetrahedra. So not triangles on the surface, but tetrahedra volumes in 3 dimensions. And you can see some things here near this edge here, the leading edge of the airplane wing. Very, very dense grids because a lot of stuff is happening there. So huge differences in pressure and so on. You can actually see the pressure distribution on the wing here. Blue is very low pressure. Why would the top of an airplane wing have very low pressure? Well, they're better. If it wasn't, we would be in real trouble. Yeah, because it's the pressure difference between the top of the wing and the bottom of the wing that keeps this plane up. And so we like seeing very, very low pressure here. And these low pressure areas, the true low pressure areas where most of this lift is actually near the front of the airplane wing. Okay? So if the back of the airplane wing damages a little bit, don't worry too much when you're looking out and you see that fall off or break. But if the front falls off, you better get out. Okay?